Hi, my name is Kritik Alapati, and this is my presentation on Lab 3, Magnetic Field of a Bar Magnet. So the objective of this lab was to understand how the magnetic field of a bar magnet works by using a magnometer on a cell phone to examine how the field changes with distance. We can do this by using the Biot-Savart law in a computational model to compare how the experimental data compares to the expected magnetic field from the model. So the results from the experimental were that n equals negative 2.7501, mu equals negative 13.695, and the magnitude of the magnetic field on axis was 1.28 times 10 to the negative 6. So the concepts and formulas we'll use in this lab have been shown below. The Biot-Savart law equation has been shown, and then you have the distance dependence of magnetic field of a bar magnet to find the magnitude. And then you have the formula for linearization that we'll use for the graph once we find our experimental data. So the initial conditions in experimental design are shown here. The system is the bar magnet and the surroundings of the universe surrounding the bar magnet. So for the procedure, I downloaded a magnometer app and determined the location of the chip in the phone using the magnet, and then lined up the phone towards north so that the magnetic field from the Earth is 0 and there was no interference. And then I measured the perpendicular and on-axis distances between the phone chip and the bar magnet, as well as the magnetic field. And for the on-axis, this was done at different distances to see how this would change the magnetic field. So the bar magnet is represented as a dipole in order to apply the Biot-Savart law. That's our assumption here. And the initial conditions are that the phone is facing north and the bar magnet is aligned with the magnometer. Here you can see the experimental data. On the left, in the top left, in the yellow, you can see the distances measured on axis as well as the magnetic field from those distances. And in the blue, you can see the average values of the distances in the magnetic fields, which were then linearized in this graph here to get a slope formula so we could get the n and the mu values. And the off-axis field was also measured. You have the distances perpendicular measured, as well as the magnetic field in the y-axis by Earth, and the magnetic field on the x-axis, and the magnetic field on the y measured, which was then corrected for by the Earth's magnetic field. And then finally, you have the magnetic field in the z direction. And all the way on the right, you can see the net magnetic field in the perpendicular. So there's a couple of experimental observations, the first being that as the distance between the magnometer and the magnet decreased, the x component of the magnetic field increased. And at very large distances, the x component of the magnetic field is approximately 0. So here are the calculations that I did for the experimental data. You can see the distance-dependent formula and the linearization formula were used to calculate k, and n is the slope, to determine n and k. So n is the slope here, and k is the y-intercept value from that linearization on the graph. And then to find mu, we use the magnitude of the magnetic field and the Biot-Savart law by treating it like a dipole. So from that, we get mu equals 5.654. So this is the first part of the code. On the left, you can see the magnet creating the magnet in the code, as well as the magnitude of the magnetic moment. And below that is the function for the magnetic field. On the right side, you can see the scale for the arrows, the distance away from the origin that the arrows are placed, as well as the observation locations of the arrows. For the second part of the code, on the left, you can see the drawing of the 2 on-axis arrows and the 4 perpendicular arrows. And on the right side, you have the values for the distance perpendicular, the average distance measured. And you have your observation location at 45 degrees, as well as your arrow at 45 degrees, and then the return statements for the magnetic field and the magnitude of the magnetic field. So here in the GlowScript model, you can see the arrows that we drew earlier. The orange ones are the on-axis arrows, the blue ones are the perpendicular arrows. And then in purple on the top right, you can see the magnetic field arrow at a 45-degree angle. So the on-axis magnitude and the perpendicular magnitudes were both larger than the experimental calculations. And this could be due to either the phone not being exactly aligned with true north and there was interference from the Earth's magnetic field, or there could be human error in the measurement of distances. So either of these could have caused that issue with the magnetic field in the model being larger than the calculated magnetic field. So what if the experiment hadn't compensated for magnetic north and there was an angle with the Earth's magnetic field? Well, the results would be skewed. If magnetic north is not compensated for, the magnetic field of Earth would be registered by the magnometer and it would alter the data. What if you were to stick two identical magnets together end to end and run the experiment again? Well, the only difference in measurements would be an increase in the magnitude of the magnetic field since there are two magnets now, but the direction of the magnetic field would stay exactly the same.